Welcome to the Ontario High School video podcast series. It has to do with use of the Nernst equation in the broader subject of electrochemistry, oxidation reduction, and so on. We're going to do part 2 of the Nernst equation podcast series, and it's the solution to part B of the sample problem that was addressed in part A. If you've not watched, or in part 1, if you've not watched the part 1 of the Nernst equation video podcast, you need to go back and watch that, or this particular one won't make a lot of sense to you. So, welcome. The problem that we were looking at, we solved part A of already. Part B of the problem was to find the concentration of nickel 2 plus when E of the cell is 0.03 volts. So that's what we're doing here. So what we're showing is the reaction at the anode, the reaction at the cathode using standard cell notation, and then our data table. We know that E of the cell is 0.03 volts. The E of the cell under standard conditions is 0.04 volts. N is equal to 2 moles of electrons. Our initial concentration of nickel was 0.80 moles per liter. Our initial concentration of cobalt 2 plus was 0.20 moles per liter. We need to find the final concentration of our nickel 2 plus, and while we're at it, in order to do that, we're going to go ahead and solve for the final concentration of our cobalt 2 plus. Well, when we go to solve for this, we need to solve for Q first. So we look at our base equation. E of the cell is equal to E of the cell under standard conditions minus our 0.0592 volts divided by N times the log of Q. And we're going to just go ahead and rearrange this equation, and I'll go through it step by step so that we can get Q isolated. So our first step is to add 0.0592 volts divided by N to times the log of Q to both sides of the equation. So it cancels on the right, and we end up with E of the cell plus 0.0592 volts divided by N times the log of Q is equal to E of the cell under standard conditions. We want to continue rearranging, so we're going to get the expression of the 0.0592 volts over N times the log of Q by itself by by subtracting E of the cell from both sides. When we do that, on the left side we'll have 0.0592 volts divided by N times the log of Q is equal to E of the cell under standard conditions minus E of the cell. Continuing to rearrange, next we're going to isolate the log of Q by dividing both sides by the factor 0.0592 volts divided by N. And when we do that, we'll have the log of Q is equal to, on top, parenthetically, E0 of the cell, or the standard energy of the cell, minus E of the cell under these conditions, divided by the factor 0.0592 volts divided by N. Next, in rearranging, we want to we just want to get rid of the logarithm. And we can do that by taking 10 raised to both sides of the equation. So 10 raised to the log of Q is equal to Q, and 10 raised to the expression of, on top, the standard energy of the cell minus E of the cell divided by 0.0592 volts divided by N. So we have Q isolated now, and we can go ahead and solve using that expression for the value of Q. We're going to substitute our numbers into our equation and make it a working equation here. So 10 raised to the quantity of, in parentheses, 0.04 volts minus 0.03 volts divided by the expression 0.0592 volts divided by 2 is equal to 2.2. And I want to show you, just as we simplified that, Q is equal to 10 raised to 0.3378, and that gives us our value of Q of 2.2. If when you went to solve for this, if you did not get 0.3378, it means you probably did something wrong in your order of operations on your calculator, so be very careful with that. Now that we have the value for Q, we can set up a BCA chart to get us ready for the reaction quotient expression so that we can solve for that value for nickel 2 plus. So before we began the reaction, we had 0.80 moles per liter of nickel 2 plus and 0.20 moles per liter of cobalt 2 plus. The change for the nickel 2 plus is going to be by minus x because the coefficients of both of these are 1, so they'll change by the same amount. For the cobalt 2 plus, it'll be plus x. So the after point, or the point at which we're going to study this reaction, the concentration of nickel 2 plus will be 0.80 minus x, and for cobalt 2 plus will be 0.20 plus x. This could have very easily been labeled actually as an ICE chart for initial change and the concentrations at equilibrium. I just arbitrarily chose the BCA method of expression. So either way, you're good to go as long as you end up with this. Now that I have my values at the equilibrium point, I want to solve for x. So Q is equal to 2.2. I set it up to the concentration of cobalt 2 plus divided by the concentration of nickel 2 plus. So Q is equal to 0.20 plus x divided by 0.80 minus x. Well, you're probably wondering why you're looking at a reprise of the previous slide, and I have no good explanation for you other than it looks really nice. So enjoy this. We're just about to solve for x. So here is how we solve for x. I take both sides of the equation and multiply by 0.80 minus x. And so I get 2.2 times 0.80 minus x is equal to 0.20 plus x. I simplify that. 1.76 minus 2.2x is equal to 0.20 plus x. And then I rearrange so that I get like terms on each side. So 1.76 minus 0.20 is equal to x plus 2.2x. When I combine my like terms, I get 1.56 is equal to 3.2x. So x is equal to 1.56 divided by 3.2. So our change in the concentrations is going to be equal to 0.4875 moles per liter. Now that I know x, I can go ahead and find what my final concentrations of the cobalt 2 plus and the nickel 2 plus are. For my cobalt 2 plus, I'm going to take 0.20 plus x, so 0.20 plus 0.4875 is equal to a final concentration in moles per liter of my cobalt 2 plus ion is equal to 0.69 moles per liter. My final concentration of nickel 2 plus would be 0.80 minus x, which is 0.80 minus 0.4875, which is equal to 0.31 moles per liter. And finally, what this tells me is that the concentration of nickel 2 plus is equal to 0.31 moles per liter when the energy of the cell is equal to 0.03 volts. Well, this is the end of part 2 of the Nernst equation 3-part series, which is part of a much broader series dealing with electrochemistry. I want to leave you with a quote. You're probably getting very familiar now with Benjamin Disraeli, great British statesman from some time ago. Circumstances are beyond human control, but our conduct is in our own power. I wish you well.